Normally I would read out the entire blurb for the talk, but our speaker has pointed out that that isn't necessary because you would have read it before you came, which is actually a valid point. But I will say things about our speaker that weren't in the blurb. So our speaker tonight is Professor Richard Easther, who is a professor of physics for his sins at the University of Auckland. I always say for his sins, I don't know what his sins are, but I'm sure he's done some.
Terrible ones, terrible ones.
So he was educated at University of Canterbury, we'll forgive him, and after that, after doing his PhD there, he had postdoc fellows at Waseda in Japan and Brown in Columbia in the US. He taught at Yale. I thought I'd check before I got it wrong. From 2004 to 2011, when he came to University of Auckland to be Professor of Physics and Head of Department, which he did for 9 years. That must have been his sin. And as of February, he's a free-ish man. And JJ Eldridge, who presented our first cafe last year, is the new head of physics at Auckland. So clearly, doing a cafe is really good for your career. Hint for people out there. So Richard's work focuses on the physics of the early universe. He explores the cosmological implications of string theory and the inflationary epoch. He describes himself as a theoretical cosmologist, which leads to very interesting Facebook ads. And he has been a TEDx speaker. So I'm sure he'll handle everything we can throw at him tonight. So if you'd like to bring your hands together and welcome our speaker, I'll hand over to him now.
Yeah, thanks hugely. I guess it's always I say for my sins, and as you say, I was head of department at Auckland for 9 years, and they say don't do the crime if you can't do the time. I've done the time, and I still don't know what the crime was, but I guess I'll find out one day. Virtually, firstly, I just want to thank everyone for coming tonight. It's always a real pleasure to talk to people who are enthusiastic about what we do. I want to start actually by asking a question. And the question is this: if I was to say the phrase "theory of everything," what kind of, if we do a kind of free association football, what would that, what thoughts would that pull out of the room? If I said the theory of everything, go. Someone's got to say something, otherwise it's going to be a very quiet night.
The gut. Gravity and quarks.
Gut. Gravity and quarks. Yes. What else? What? Didn't hear that.
The movie Theory of Everything.
The movie Theory of Everything. String theory, quantum gravity, all of these kind of cool, kind of catchy things. And so the interesting thing about that is that the phrase that you hear is an equation that you can write on a T-shirt that explains everything that happens in the universe. And so that's a thing to strive for. And it's something, we're a reasonable way from it. You hear names like Hawking and Einstein. There's been people who have given large chunks of their careers to try, unsuccessfully so far, to figure out what that might be. But I want to take us back to a time where we really didn't have a theory of anything. And so that time would be the time when Isaac Newton was a student. And there was a time while Isaac Newton was a student when Cambridge was closed. The University of Cambridge was closed because of a plague. And that may or may not strike a chord with people in the room.
We know it well.
And so he went home to his family farm during that time. And so there were lots of jokes this time last year about how, plague has closed our universities. Newton was home for a year. He came up with all kinds of brilliant ideas. And those jokes, I have to say, seem a little less funny a year later than they did at the time. But here we are. Anyway, Newton went home for the year, and the story has it is that he was sitting in the orchard. And while he was sitting in the orchard, various versions of the story, he saw an apple fall, or an apple was to kind of personally conk him on the head. And I don't know whether this story is true or not, but I do know that if you go to the University of Cambridge and you go to Trinity College, they have an apple tree that they swear up and down is the original apple tree. Obviously there's been a fair bit of pruning, some seeds have been grown, but it's basically the same apple tree that Isaac sat under all those years ago in the 1660s. 1660s, I think. Yeah. Yep. And so here we are, where we're trying to make sense of, what it is that Newton figured out. We're trying to figure out how the world looks different to him before he does this, and how the world comes to look different to him and others after he has this insight. And so the insight is, I didn't bring an apple tonight because I don't want to throw apples around the room, because that's a bad use of an apple. And then I realized I was going to be sitting in a room where everyone's got a glass in front of them. And so if I start throwing tennis balls around the room, obviously that could cause a bit of trouble. But I will, Scott, if this, sorry, mate. This is like the PE lesson that you thought you had skipped, and now you're having that dream where to graduate from high school you have to have a PE lesson. Brilliant, well done, thank you. I went there. Yay! I'm not going to do it again.
I don't think my balance is that good.
The realization that Newton had was that the same rules that make the apple fall from the tree, the same rules that control the arc of the ball as I throw it through the air, those are the same rules, the same forces, the same equations that keep the planets in orbit around the sun, that keep the moon in orbit around the earth, that rise the tides twice a day, all of the things that we see in the solar system, or we have come to understand in the solar system. Remember, this is 60 or 70 years after Galileo, after Tycho Brahe, after Kepler. So we know that the planets most likely go around the sun, but we don't know why they go around the sun. We don't know what the nature of the force is that keeps the planets in orbit around the sun, that causes them to move in the way that they do. And so the answer that Newton comes up for that is the force of gravity. He explains the properties of the force of gravity as something that gets weaker as you move further away from the object, that this force is proportional to the mass of the object, whatever the mass might be. In some sense, that maybe defines the mass. But Newton was able, starting from these equations, he was able to say the same thing that controls, a rock, two rocks falling from the Leaning Tower of Pisa, the arc of a ball thrown through the air, the trajectory of a cannonball. Those are the same rules, the same things, exactly the same things that control what happens in the solar system. And we can use the math that Newton developed. Everyone else thinks that calculus is somehow invented to make physics hard. But in fact, Newton invented calculus to make physics easier. He had to create new math in order to have these ideas. He realized that these same ideas were able to be used to explain what we see in the solar system. And that is actually a profound change of perspective and a change of understanding, particularly in the European mindset at that time, where you make a distinction between the sacred and profane, between the earth and the heavens. And you realize that the same rules are in fact applicable in the sky as they are on the ground. This is a huge wrench. And so it isn't so much a theory of everything, but it's certainly getting to the point of being a theory of everywhere. You've suddenly got to the point where we can carry out experiments on Earth, we can measure things on Earth, we can extrapolate that knowledge into the sky. And so this gets us to the beginning of the 1700s. And so what I wanted to do was just to kind of establish the sense that we have this thing called gravity, that we have rules that objects obey, and that physicists have been able to write those rules down, for some hundreds of years. And so we look at the planets, and the next step beyond the planets is the stars, right? And so one of the common inheritances of humanity is the ability to go outside and to describe the night sky, to say what we see there. And so up until fairly recently, when electric light in cities became ubiquitous, almost anyone would have had the experience of looking up at night, or being able to look up at night and seeing this kind of stripe of light across the sky that we call the Milky Way. We're particularly lucky in Aotearoa, New Zealand, to be able to do this. We have nice clean skies. We have dark nights. Even inside of the city, if you're in a park inside of in Auckland, you can go out on a moonless night. You can see the Milky Way. Go to the beach. You sit on the beach for 20 minutes. You let your eyes adapt to the dark, and you see just this wondrous sight that 100,000 years ago, when the first when early hominids looked up into the sky, they would have seen something very, very similar to that. In exactly the same way that we have been able to make sense of the solar system, we have also come to make sense of the object that we call the Milky Way. And so the trick with the Milky Way is we look at that with a telescope and we realize that it isn't just a patch of light. that it's actually tens of hundreds, and in fact hundreds of millions, billions of stars. And so we look at this object and we ask the same question, do we understand the dynamics, motion of these stars in the same way that we can understand the dynamics and motion of the solar system? And that seems like a simple question, why wouldn't that be the case? And there's two reasons why that might not be the case. The first reason is that in the solar system, we can see pretty much everything that there is. And so this doesn't sound like a complicated thing to say. We look into the solar system, it's either the sun or it's the planets, and the planets shine. They're relatively easy to find, at least the big ones, because they shine from the light that's been reflected off them by the sun. But imagine if there are other, we don't know that there aren't other objects in the galaxy that aren't, we could get exotic and we could talk about black holes. And if you want, if you've got question time, I can tell you something cool about black holes and someone who was talking about something very similar to them in 1780 using purely Newtonian ideas. But we can also take the sense that we've got, is everything that we see in the sky also everything that's there. And so we're in the position of people watching a game on TV, a sport that they've never seen before, a sport that they don't understand. And they're trying to make sense. They're trying to come up with the reasons why the things that they see on the field are the things that are taking place. And so there are two things you need to be sure about. The first thing you need to say, well, I can see all the players, but I don't necessarily know the rules that control them. Alternatively, you could imagine a situation where you knew the rules, but you couldn't see all the players. In other words, there were things happening on the field that didn't make a lot of sense, but they would make sense if you had a better view of the game that was being played. And so when we look into space, we actually realize that there are two things going on. The first question is, do the laws of physics, as we test them on Earth, as we have come to test them in the solar system, do those same laws of physics apply on scales that are equivalent to the distance to the stars and beyond? And then, the answer seems like, the default answer maybe is yes. We've got used to this idea that we could just assume that everything's the same out to the edge of the universe. But we don't know that until we test it. The flip side of it is, if we want to understand how gravity works, we've got to know what's there in order to figure out what's providing the source of the gravitational force, where all of the mass is. And that isn't obvious. We're looking into space, we're assuming that we can see everything, but it's not necessarily true. And so this is a challenge that was recognized, it's been recognized, in fact, for hundreds of years, but it's a challenge that's come into sharp focus for physics and astronomy over the last, certainly over the last 100 years, maybe over the last 80, particularly over the last 40 and 50. So we know that our own Milky Way galaxy is a giant kind of spiral spider of stars. Has everyone seen a picture of a galaxy? So if you haven't, let's just pause. Everyone pull out their phones, who's got phones, and Google spiral galaxy. So this is my question of whether or not I can have the prompt or not. So I didn't bring a picture of a galaxy, but everyone can pull out their phones, check to see if they got it. And if you don't have a phone with you with a picture of a spiral galaxy on, you can share it with your neighbours. Particularly, go for M81 or something like that. If you have M or M81, M51, there's some just beautiful, what they call grand design spirals. You see them edge on, face on. You see the Hubble Space Telescope photos of these objects, and they're just stunningly beautiful. And what you're looking at is the combined light of hundreds of billions of stars in many cases. When you look at them carefully, you'll see that most of the light is coming from the middle. A spiral galaxy seen edge on looks like two fried eggs that have been kind of glued to each other back to back. You've got the kind of yolk in the middle, what we call a bulge, and then you've got the thin disk, which is where the spiral arms, if you look at it face on, you're seeing the white of the galaxy and the yolk. Most of the light comes from the center, but when we look at the way the galaxies behave, and the way the galaxies move, it turns out that the outer parts of the galaxy are moving around the center at much the same speed as the inner parts of the galaxy. But if all of the mass of the galaxy was where most of the light is coming from, they shouldn't do that. The outer parts of the galaxy should move more slowly. Because just like it does in our solar system, the reason it takes Pluto so much longer, 240 years, to go around the sun relative to ours, is not just that Pluto is further away from the Earth, Sun than the Earth and has further to go, it's also that Newton tells us that Pluto goes more slowly. But in the case of the galaxy, the outer parts of the galaxy are moving pretty much at exactly the same speed as the inner parts of the galaxy as they rotate. They'll take longer to get around the galaxy because they've got further to go, but they're moving faster as they do it. And so that tells us one of two things. It tells us either there's a whole lot more stuff in the galaxies than we can see, and if there is, that's the stuff that we call dark matter, or it tells us that the laws of gravity work differently in galaxies from the way that on scales, on distances that are equivalent to the distances, the size of galaxies. So the Milky Way is maybe 100,000 light years from across. The sun is 8 light minutes away. So it's telling us that the way that we understand gravitational physics on the Earth and in the solar system, something more complex and complicated that happens on large scales. So that gets us to this question of what we're going to do or how we're going to make sense of what we see. And so the trick of this is that the other thing that has happened is that while we realize that we live in a galaxy of our own, the other thing that has happened from the 1920s onwards is we realize that our galaxy is one of many galaxies in the universe. So just as the Milky Way is a collection of maybe 100 billion stars, the visible universe contains maybe 1 trillion galaxies, each one of which is potentially an island of stars like the Milky Way. So how many people here have seen the movie Moana? Either they went themselves or they took their kids or their grandchildren. You should go and see it. It's a beautiful movie. And so Moana is a story of a little girl who's growing up on an island, and she's kind of dissatisfied with things because she thinks there should be more to life than her one island. And so she finds out that her ancestors, for whatever reason, had decided to hide the knowledge from her that her island was in fact one of many islands in this ocean. And so no one's hidden this knowledge from us. We simply had to figure it out. But we've had the same change of mental perspective than Moana had as astronomers, as people. When we look into space, we realize, firstly, that this band of light across the sky is this giant spidery two fried eggs glued together of stars. And then we realize that as many stars as there are in our galaxy, there are similar islands that are strewn through the universe. And so just as Moana realizes that she's not living on a single island that exists in an empty ocean, we've come to realize that the space, the three-dimensional ocean that we inhabit, is one of our galaxy is one of an almost limitless number of similar galaxies. So we see the universe has not only become much larger, but each of these galaxies is a laboratory that we can not perform experiments, but we are able to observe and test our ideas about the way that gravity works by watching, not the way that things move, because things move slowly enough in the galaxy that we can't see them move, but we can measure the speed of objects in the galaxy by using the Doppler effect to see how much its light has been redshifted or blueshifted. And so by looking at the relative redshift and blueshift across a galaxy, between one side of it and the other, we can get a sense of how fast the different pieces of it are moving. And so in doing that, this brings us to the 1970s when this property of galaxies was kind of teased out in detail by Vera Rubin and others. It's also true that when you look at galaxies, the galaxies themselves are not distributed at random in the sky. They're in fact the galaxies themselves live in clusters. So people have got their phones out, they can Google galaxy clusters if they want. Those look pretty cool. You can do it afterwards or you can do it now, I don't mind. When you look at a galaxy cluster, the galaxies inside of a galaxy cluster are themselves moving too fast for the galaxy cluster to be a bound object if all the gravity in the galaxies is coming simply from the stars whose light we are able to see. So we see how bright a galaxy is, we know how bright a star is, we figure out how many stars must be in that galaxy, we figure out what its gravitational field would be, we then ask how fast these galaxies are moving, and they're moving way too fast for those clusters to hold together, but yet we see tons of galaxy clusters in the sky, so there must be some reason for being there. So again, we have another way of making sense, or another way of getting a hint that there's something about the universe that's telling us that there's more to the universe than we're able to see with our eyes, than is emitting light. And so this gets us to sort of close to the end of what it is that I want to say in terms of setting the stage, and I understand that we move to a Q&A. Well, where we've got to is a choice between thinking that there's more stuff in the universe, or on the other hand, thinking that there's rules to the way that the universe behaves that we don't understand. And so what I'm going to tell you is that 99% of my colleagues, including myself, have come down on the side of there being more stuff in the universe, that the universe contains large quantities of stuff that we can't see. And it's not only stuff that we can't see, it has to be stuff that isn't made out of atoms. Because even if there's stuff in the galaxy that isn't organized into stars, if it's made out of atoms, it can interact with light, it can block light, it can heat it up, we would be able to see evidence for its presence. So it has to be stuff that light is able to pass completely unhindered through it. And even the kind of the coldest, most subtle gas in the universe is going to be warmed, is going to interact with the light as it passes through it. So it has to be something that's not made out of atoms. We look not in the periodic table, but we look in the kind of the equivalent to the periodic table that we produce, that particle physics has given us. There is nothing in the periodic table that has the properties, the mass, the stability, that will provide the dark matter that we need to explain what we see in the universe. So we also know that whatever the dark matter is, it has to be some kind of matter that we have yet been unable to discover or produce in particle accelerators here on Earth. The alternative is simply, that we don't understand gravity at some level, and we can find ways of saying, well, okay, how would gravity need to be different? We can test the predictions of those theories against what we see. The people who advocate for those theories will point to some very odd things about the detailed nitty-gritty dynamics of galaxies and say that they can account for these more easily. The people who favour dark matter, or the vast majority of the reason that people favour dark matter, is that dark matter provides a very natural explanation for the large-scale structure of the universe. Why, for instance, that there are galaxies and galaxy clusters. That's something that's very easy to understand in a universe that's dominated by dark matter. And in fact, dark matter makes predictions, or the assumption that dark matter exists makes predictions about the distribution of galaxies in the sky that seem to be well supported by data. So at the moment, it's kind of not a draw, but the game looks like it's going very much in the direction of dark matter. The thing that we haven't done, though, is we haven't been able to answer the question as to what the dark matter might actually be. Something, again, we can pick up in the question time, but until that day happens, we know that either there's a chance that something may turn out to be different, or alternatively, there's a discovery waiting to happen that physicists are excited about the opportunity that presents. But that's my spiel as it is, and I'm told that there's time for a break and any questions, and I'll hand back to Mike and see.
Cool. All right. Well, let's start by. I'll give you back into this ball. Let's start by a round of applause for our speaker.